It's a low riding bar with a truck. Exactly. That's stuff. I could just go on. You can do that. The body line. Just put it bigger top on it. Or better with the body. It'll just be a bigger top on it.
Oh, geez. I can't make that joke because I'm recording. So, um, yeah. So we have to do this. It's a 1 day detour. So sorry, not sorry. We have to learn how to do this so that we can do the next to last task in this unit. So I don't think I ever showed you how to do this before in Algebra 1. So we have to learn how to graph absolute value functions. So I'm assuming you guys are all aware of what an absolute value is. Like the absolute value of 5 is, the absolute value of -5 is, right. So we understand that absolute value has this magical property where it effectively takes positive numbers and keeps them the same, and then it takes negative numbers and it does make them positive. And the reason it does that is because the absolute value function is like a little calculator that calculates a number's distance away from 0. And since distances cannot be negative, that's why absolute values always regurgitate positive, or a 0 at the worst. So you got this lecture months ago when we did our absolute value. Remember the swishers and splitters and all that. So you're familiar with it in that sense. What we have to talk about today is how to make a graph of an absolute value function. One of our standards that we have to ace, not pass, but ace, is can I graph a nonlinear system, a mixed system like we've been doing, where one of the functions is an absolute value function. So we begin by just thinking about or talking about just a general y equals the absolute value of x. So this is a parent function. So what we're going to look at first, this will not take long at all. I mean, I shouldn't say stuff like that because, I jinx myself, but this should be a simple lesson for you guys. So just a kind of a little bump in the road, we'll get by it, and then tomorrow we get back to nonlinear systems again. So to graph the absolute value function, I'm just going to walk through with you how it comes to exist. I won't do this every time because there are shortcuts, but I want you to have some understanding of where the graph comes from. So we're going to start by making just a good old-fashioned table. And this is something we do a lot of in pre-calculus where, and I should do more of this in Algebra 1, where if I forget how to graph something, because there comes a point where there's so many kinds of graphs. There's square root graphs and quadratics and lines and absolute values and cubics and roots and all these things. And when I forget, not if, but when I forget what a family of different functions looks like, I can always do this, the oldest of the old school, and that is just make a table. It's a good old-fashioned matter of plug in an X and get out a Y. And you can use this, and we'll start to use this more as the math gets harder and harder. We're doing it a lot right now in pre-calc where we have to find a lot of different X and Y values to piece together what these really complicated graphs look like. And so a good old-fashioned table will get us far. So we're going to start with, I hope, the obvious choice, and that is 0. So this is how a graph comes to life, is we look at it, we don't, if I didn't care about you, I would just say, hey, the graph looks like this, boom, suckers, get her done. But I want you to have this sort of thinking and reserve so that if you forget, then you go, I can do this. I know how to rebuild it. So if I put 0 into the equation for x, what do I get back for y? Yes, because the absolute value of 0 is 0. Now let's start moving in the positive direction. If I head to 1, if I put 1 in place of x, what do I get back for y? 1, right? Because the absolute value of 1 is 1. Anybody confused as to what I'm doing right now? Just changing x's into whatever I want. Like I'm the boss of the table. I can put in whatever I want. Like I could put in 4. What's the absolute value of 4? 4. So if we were just to graph that side of the table, we would see a function that has points here here, and I believe here. So far, so it makes sense, right? And it looks like a straight line at this point in time. But this is where absolute value shows itself. And it says, hold on, slow your roll a little bit, because if I head to the other side of the table now, if I go in the negative direction, what's the absolute value of -1? Right. So you see that if I put a negative number in there in place of x, the absolute value machine does what it does, and it takes the absolute value of my negative input and it gives me back a positive output. Likewise, if I put in something like -3, what does it give me back? Good. And so on and so forth. And so what we see is something that kind of has the same structure for different reasons, kind of, but the same sort of structure as a parabola, like a quadratic. How if we took something like y equals x squared, I wouldn't write that down, but if I took a function like that, we've seen this before where if we put positive numbers in it, it squares them and keeps them positive. But if we put negative numbers in, it squares them up and flips them back to positive. And that's where that parabolic sort of shape comes from. So this function mimics that. So we can also go to the left side and say, okay, so if I go left 1, I go up 1. And if I go left 3, I go up 3. And what we realize now is that it's not a straight line, but rather a V. And I don't think that you and I together in our experience have ever seen a function graph like this. But this is what the family of absolute value graphs look like. And if you connect the dots like this, put an arrowhead on both sides, you get your very first absolute value graph. And this is the parent function. What that means is that as over the next 10 minutes or so, as we look at different modifications we can make, all the other absolute value graphs are just versions of this. They're going to be skinnier, maybe fatter. They're going to move around. They might flip upside down, but they're all going to be derived from this parent function. So any questions about that? Okay. So what we need to do now is talk about what happens when we start modifying. And you could make this as difficult as you want, but I'm going to try to make it as simple as I can. So we're going to see 4 different types of what we call transformations. And so the first one that we're going to see is we're going to leave the absolute value alone, but we're going to stick a modifier at the end of it like this. Notice that the modifier is not a part of the absolute value. As we do more with graphing families of functions, it's what I come to refer to as an afterthought. Whenever you put a plus or a minus after the business part of a function, it's an afterthought. So basically, the function grinds out all your input-output stuff, but every time before it gives you an answer, it takes away 3. Would anyone like to venture a guess as to what that's going to do to the graph? It's going to do exactly what you just showed me with your hand. Correct. It's going to take the entire graph and it's going to literally move every point down 3 units. It's not going to get changed structurally. It's just going to move. So if we were to graph y equals the absolute value of x minus 3, then we just take the parent function, we regraph it. I'm going to zoom in a little bit. We regraph it, but we graph it shifted down 3 units. And so my vertex is no longer at 0, 0. I go down 1, 2. Oopsie, excuse me. That was an accidental tap. 1, 2, 3, and it's right there. And if you don't want to, and you shouldn't want to, you don't have to make another table for this because you know what the parent function is going to look like, right? You know it's going to have an arm that heads up in the northeast direction like this, and it's going to have another arm that heads up in the northwest direction like this. So that is what we call a vertical shift. That's the technical name for it, but you can call it whatever you'd like. But any plus or minus after a function is going to cause it to shift up and down. It doesn't change it, make it skinny, fat, doesn't move it sideways, just moves it up and down. What do you suppose would happen if we did something like y equals the absolute value of x, shut it down, plus 2? What's that going to do? It'd just go up 2. So if I asked you to graph that, then you would just do the same thing, except you'd start at the 0, the home base normally, and you'd go up 1, 2, put a dot, and then you'd know that your arms are going to go out like this and out like this. Sorry for the bad drawing, but any questions on the vertical shift? Okay, so let's take a look at another type of shift. So that's 1 down, 3 to go. The next thing we're going to see is inside the absolute value. And this is important because it's inside what we call the argument of the function. It's like the business part of the function. So if I took and put a modifier in here like this, it is not an afterthought. This is not going to be something that we think about later. This interferes with the business part of the function. I don't get to just go about my business and then find some number and then just move it down 3. Does anyone want to take a guess as to what this one's going to do? It doesn't actually affect it structurally, believe it or not. Let's take a look at this so you can discover this real quick. I won't make this take long, but let's make a quick table. So I'm going to pick some numbers for you. I'd like to do 1, 2, 3, 4, and 5. I'd like your help with this. I'm terrible with the math, the numbers, and the calculations. They vex me. So if I were to take 1 and put it inside the absolute value, right where this little red arrow is pointing up here, what is 1 minus 3? -2. But what's the absolute value of -2? So we feed this function a 1, it gives us back a 2. And again, this is something you can be empowered to always make a graph. No one should ever stare at a function and go, I don't know how to graph this. It's like, make a table, right? So let's feed it a 2. Put a 2 where the little arrow is pointing. What's 2 minus 3? The absolute value of -1 is 1. So I feed it a 2. It gives me a 1. What happens if I feed it as a 3? I get 0, which the absolute value of 0 is just 0. And this is where it happens. Watch what happens. If we feed it a 4, what's 4 minus 3? The absolute value of 1 is, and it started its bounce back. Okay, so there's always going to be that centering point where the V hits bottom and shoots back up like a what's the word? Reflected, like a reflected laser beam or something like that. Science teachers would probably tell me there might be a better word for that, but something like that. And same idea, if you put in a 5, what's 5 minus 3? 2, and the absolute value of 2 is 2. So if we were to make a graph of this one, we would see this. My first point is at 1, 2. Second point is at 2, 1. Third point is at 3, 0. And this now is where the bounce occurs. Seeing the graph now, and you can do this on an ACT, you could do this on any test. There's nothing stopping you from making a table. That would take you 30 seconds without me talking so much. And so when you see the graph like that, I would ask you again now, what did the -3 inside the absolute value physically do to the graph? It shifted it to the right 3, which is somewhat counterintuitive. Like most people, once they figure out that, hold on a second, so are you telling me that this number inside is a horizontal shifter? Yes, that's what I'm telling you. But it's backwards of what your brain tells you. Once you figure that out, a normal person would say, oh, so it should go to the left 3. It actually moves the opposite direction. So we just take the parent function and we shift it to the right 3 units. Easy peasy, right? Let's do another example real quick without a table. What do you think would happen if we graphed y equals the absolute value of x plus 5? It would shift to the left 5 units. And again, I don't need a table now because I understand what the graph looks like. I'm just going to start back at my home base. I'm going to go left 1, 2, 3, 4, 5. I'm going to plant my vertex, and then I'm going to make my graph. And that is the end of that. Okay. So far what you have learned, I hope, is that a number that's after the absolute value will cause your graph to go up and down intuitively. Plus means up, minus means down. A number inside is going to cause your graph to shift sideways counterintuitively. Plus means left, go figure, minus means right. Any questions so far? Okay, so there are 2 remaining transformations that we need to talk about. There's another one that we're going to avoid. But the one that we need to discuss is this. Oops, my bad. I forgot to switch to the pen. Would anyone like to take a guess as to what that number is going to do? Eventually, I'm going to have you, it's not difficult, but eventually I'm going to throw all 4 modifiers or transformations at you. What do you suppose this one does? Let's find out. Let's make a quick table. I could just tell you, but again, I want you to sort of see it for yourself. And let's do the same numbers again. Let's do -2, -1, 0, 1, and 2, because we're centered. This one will not move. FYI. Does something to it physically, structurally, and you'll see. So let's put a -2 in there in the absolute value. So again, where the little red arrow is pointing, we're just going to change that into some numbers. If you put -2 there, what's the absolute value of -2? 2. And what's 2 times 2? Correct. So an input of -2 gives an output of +4. Let's put a -1 in there. What's the absolute value of -1? 1. And what's 2 times 1? 2. Interesting. Put in 0. The absolute value of 0 is 0. 2 times 0 is 0. And we have found our bounce point because here it goes. If you put 1 in there, what's the absolute value of 1? And 2 times 1 is, and there's the bounce. And as you would predict, if you put in 2, you get a 2. 2 times 2 is 4. So let's take a look at the graph. Zoom in on that just a little bit. So we figured out that what was our output at -2? When we went left 2, what did we get? On your table, left -2, output of 4. 1, 2, 3, 4. Sweet. And when we put in -1, what did we get? 2. And when we put in 0, 0. When we put in 1, when we put in 2. So I could create the graph. I mean, it's sort of inconsequential at this point in time, but the point is that something happened. The graph didn't move. It didn't move left. It didn't move right. What happened to it? It sort of got it's what we call, FYI, a vertical stretch. It feels like someone took their hands and compressed it from the sides, but that's actually not the same. What happened was all of the Y values got doubled by 2. And if you could picture like some math god hand reaching in and grabbing the original V, taking all the points and pulling them up like silly putty, that's what we call a vertical stretch. And that happened because of the number that was in the front. So I ask you again, these are just questions that show me that you understand. What would happen if I did something like this? It would look fatter now, because what happens now is all of the Y values, rather than being stretched up times a whole number, they're being stretched times a fraction. And as you know from like 5th grade, when you multiply numbers by fractions, they actually get smaller. So in a case like this, if I graphed this, my first point would still be at 0, 0. I don't know why there it is. And this time when I go out 1, I'd only go up 1/4 of the way. And when I go out 2, I'd go up to 1/2. And when I go out, so on and so forth. It would take me all the way out to 4 before I could get up to 1. And that is not called a vertical stretch. That is called a vertical compression. And so the graph this time would look like this. So that's 3 transformations down and 1 to go. We've learned that a number outside is an afterthought, movey, uppy, downy. A number inside is a horizontal mover, counterintuitive. And a number in front is a stretch or a compression. Stretch if it's bigger than 1, compression if it's less than 1, which leads us then to the last guy. And the last guy is a negative. And you'll probably figure this one out, but would anyone like to guess what happens if I put a negative in front of the absolute value? Exactly. It's going to flip it down. And you think, again, it makes perfect logical sense that all of the Y values, any number you put in front of an absolute value is going to toy with it. And that goes for all functions. It toys with things vertically height-wise. It multiplies them by stuff. And as you know, when we take numbers and we multiply them by -1, they switch signs. Positives become negatives. And so here is what the graph would look like by default. And so this is not the graph that I want you to see, but this is what the parent function would look like. It would go up at that perfect rate of 1/1, the fraction 1/1 like that. So that's the parent function. The graph of the negative would still have the same vertex here, but its arms would go downwards like this. So it's going to spawn from the same place, but it's going to go downhill like this. So the goal here, the end game, we're almost done, is to get you now to be able to make a graph when all four transformations are in play. So let's take a look at a couple of those and then I'll shut up. Sound good? Okay. So let's take a look at, I'll just put them all in here at once. No sense in, it's like a cold swimming pool. You don't sit there and dip your toe in it and make a bunch of noises. If you want to get in and go swimming, you just jump in, right? So let's just jump in. So let's say I gave you a function like y equals -2 times the absolute value of x plus 3 plus 4. So there's all four transformations working in harmonious unison, right? So we have to do things in a very particular order. First of all, where's it going to move to? Correct. So the normal vertex would be here in the center at 0, 0, but we're going to follow these directives. This one, you guys all know, is a leftward motion of 3. You also know that this number is an upward motion of 4. So I'm going to begin by just finding my home base. That's like job one, is go find your new home. So I'm going to start from the vertex, the origin, and I'm going to go left 1, 2, 3, and up 1, 2, 3, 4. And I'm going to say, okay, my V, or my whatever you call that, it starts from there. Now let's talk about the other transformations. What are the negative and the 2 together going to do? What's the negative going to do? It's going to make it into like a peak instead of a V. And what's the 2 going to do? It's going to make it slimmer. It's going to make it so that when I go out 1, I don't just go down the normal 1. I go out 1 and I go down twice as much, 2. And I just keep utilizing that slope of 2 or -2, depending on which direction I'm going, like that. And that's how quick and easy it is to graph an absolute value function. You just utilize your 4, sometimes not all 4. You just utilize your transformations, go to your home base, and then build the function from there. Okay, how about this one? Let's do y equals 1/2 times the absolute value of x minus 2 minus 1. Where would I go first? Right 2, down 1. That's step 1, is go find your home base. So I'm going to go right 2, and I'm going to go down 1, and I'm going to mark my vertex right there with a point. Now, how many more modifications are there? Just one in this case, right? We don't have a negative transformation, so we don't have to flip it down to a peak. It's going to stay as a V. And if you want to know how to build these things, the trick is that this number, you remember this from Algebra 1, that number is going to be the slope of your arms. And so like if I left, let me zoom in on this a little bit for you here, but like if I leave the vertex and I know that my graph says 1/2 in front, then I just use what we learned in Algebra 1 and I just go, look, slope is up 1, right 2, up 1, right 2, up 1, right 2. And then I do it in the other direction, make a -1/2 slope. I go up 1, out 2, up 1, left 2, out 2. You just keep doing that over and over again. And then you connect it, put arrowheads on it, and you got yourself a graph. You think you can do this? Because this, I didn't want to take a whole day for this, and I was like, let's just make sure. So today, all I'm going to do is give you a worksheet, and all you're going to do is graph 8 absolute value functions. It should take you 15 minutes or so. And then tomorrow, we'll come back in, and we'll start combining this with the other stuff. Sound good? All right, cool. I got to, there it is. It's right there. All right, I'm going to pause this, and if you have questions, then I'll go over them with you.